Hello everyone. Welcome in the third episode about .NET GC internals. So we are live online and ready for gaining a new piece of knowledge about .NET GC and internals. It's 7 p.m. here in Central European time. The Steam Game Festival has started just a minute before, so you have hundreds of demos on the Steam page. So if you are playing games, please wait 1 hour and go to the Steam page after this webinar, not during this webinar. And okay, so let's just proceed. Say from where you are. I'm always happy to see that you are from various places, so just say hello on the chat and say from where you are, wave a hand, and just let's proceed then. So today we have the Concurrent Mark phase episode, the third one in a row. The whole thing is, as maybe you are watching this for the very first time or so, the whole thing is about 9 or 10 or something around that number episodes about the .NET GC internals. So we will cover various phases of it. We have covered so far the Mark phase, which was pretty important one. We have also the introduction, the very first one episode, and now today we are covering the Concurrent Mark phase, a slightly less, maybe smaller, maybe we can say that's smaller module, because it is just a kind of the difference and the kind of variation of the regular Mark phase. So it is not as big as the as for example Mark phase. So today we will cover things like decode such a cryptic things like mark array, concurrent visiting of objects, floating garbage, what it is, WriteWatch List, and so on and so on. And as always, I'm super inviting you to ask questions. Do not hesitate to ask questions if something is not clear. I'm trying to be clear, but obviously I'm not always able to be, and I'm not always I am able to be so clear as I would like to be. Also, maybe you have some questions why something is implemented in that or that manner. I will try to answer all the questions now during the webinar, or maybe I will just gain a knowledge and answer in the future in a blog post or in the next episode. So do not hesitate to ask any questions. That's the main message. Okay, so Concurrent Mark phase is today's topic. As we said in the previous episode, the Mark phase, just in 1 or 2 sentences, the goal of the Mark phase is to discover what is reachable. So we need to know at the GC time what should be garbage collected. So in other words, we would like to know what is not to be collected, because it is still in use. In terms of the GC, it means something is reachable, it cannot be reclaimed. So the Mark phase was the one responsible for discovering that, discover what is reachable, and it was it is based in most, or maybe in all algorithms, it is based on traversal of the graph. So we have the object graph, we traverse this graph, we mark objects that we are visiting, and in the end, after traversing everything that we can traverse, we know which objects are reachable. They have this mark pin set. And that was pretty easy in times of non-concurrent version that I described to you last week, because it was in a time when everything was paused. So the whole application was paused. So the state of the object graph was not changing. And it was a pretty nice thing for the GC, because it could safely traverse the whole graph and no one interrupted. It was just this paused state of the whole object graph that we can traverse. So that's pretty easy, let's say. And then in the concurrent mark phase, it is another way of marking objects, which is just being done when the whole application is running. So the concurrent mark phase, as the name states, is about discovering the reachability of objects while the application is running, which means the concurrent GC needs somehow marked objects while the references between objects are changing, which seems to be a pretty complex thing, because you know, when the application is running, it means that every reference may change. So it is that, okay, the GC is starting with such graph, but it starts and it tries to traverse this graph while your code is changing references. So for example, in the middle of the GC, when the graph is being traversed, it may happen that object A has no longer reference to B, or maybe we have changed it to another new object B, or maybe we have changed this one to something else. Everything that maybe happened changed, and so on and so on. So it looks like a mess that we are traveling to do all that stuff while all these things that we are trying to navigate through and we are traversing is just constantly being changed. That's a pretty big topic. And we have, when we try to understand what are the main problems here, we will end up with the conclusion that there will be mostly two problems. First of all, maybe a little bit smaller problem would be that okay, we need somehow to mark object while the object is being used. So this is a first problem, because as we remember, the mark bit in case of the non-current mark phase is just a bit inside an address in a method table. So just to recall that every object as shown here in details looks that it is just an object in a memory, and it consists of those three important parts. And imagine that this is this B object drawn in details, and it has a header, it has a method table pointer, and a data. It is always like that for objects, you know, on the heap. Sorry. And the mark bit is set here inside the method table pointer, which was pretty strange because method table pointer, as the name states, is a pointer, so it points to some data. It points to the kind of entry point to the metadata of this type. So while it is a pointer, we are changing it by setting some bit. As we know, it is the lowest bit in case of method table. It was fine because the application was paused. Nothing, there was no code trying to use this object, and that's why it was safe. But now we would like to mark the object while the object may be used, because we are running in this concurrent mode. So the problem is, if you would like to use method table again, it would be problematic, obviously, because then the method table pointer may be used and we are just simply kind of invalidating the method pointer, while other code may be interested in using this pointer. So it is not such a good idea, probably, to use a method table by itself for that purpose. And we will cover that. So this is the, let's say, smaller problem. And the bigger problem, obviously, sorry, I'm trying to get used to my new tablet with shortcuts, hard-coded to it. Okay, so the second problem is, the biggest one, is how to get a consistent view while the references are changing. As I described, everything is changing under your feet, and you are trying to navigate through those all the time changing references. This is the biggest problem for sure. So having those two problems, let's allow me to describe how you can solve those problems. Always remember about asking questions, because it is a very nice way of interaction with you. So if you are not falling asleep, ask some questions. So the problem number one, marking used objects. We can't use method table, as I said. It is a manipulation of the live pointer to the method table, which is risky. Moreover, it will be kind of cache invalidation because we need to touch every object that is marked. Maybe they are not so let's say used, though, so we should invalidate the cache that contains this object just to mark it, which probably is not so good idea either. So the solution is pretty easy. Instead of marking it inside the object, let's just create a separate space for this, an array, a data structure for remembering which objects are marked. It is not a list, like do not imagine that it is a kind of double linked list to which you are adding addresses of marked objects, because it would be too slow, because we need to maintain the whole list and preferences between and so on and so on. So instead of this, the mark array has been introduced, which is just a kind of binary bitmap, map, however you call it. It is just a continuous memory region that is a description for covering the whole managed heap, in fact. And every bit inside this mark array is responsible for remembering information that the particular memory region, the corresponding memory region, is marked. And as I said here on the slide, it depends on the runtime which we are considering. In case of 64-bit runtime, each bit inside the mark array, as shown here, each bit here is just responsible for a 16 bytes of address. So here we have the whole memory region, or the whole managed heap containing our objects. From there to there, there are all the generations, everything that can be allocated. We have covered here the whole memory region that may be used by our application. We are splitting this memory region into 16 bytes based sized memory regions, and every bit inside the mark array is saying whether this 16 bytes memory region contains marked object or not. So it is pretty simple idea. So in the end, we have every single bit describing the 16 byte memory region. In case of 32-bit runtime, it is 8 bytes. So we can say also that, okay, if the single bit covers 16 bytes, a single byte covers 128 bytes. Sometimes you can find the concept of mark word, which is just saying that 4 bits, which is a word, covers 512 bytes. The mark word is less popular concept, but in general we have this mark array, and every single bit inside is just saying, okay, this particular memory region contains a mark object. So imagine that we have object here that is just a kind of class that we are using, and during the object graph traversal we hit that, okay, we are visiting this object, and this means that, okay, this particular region that is where the beginning of this object is simply falls within, we need to set a corresponding bit inside the mark array, which will be somewhere here. So this corresponding bit will be saying that, okay, this particular memory region contains a marked object. So in the end, the mark array will be just a continuous memory region with some bits set saying, okay, this particular memory region contains, and maybe I should say have an object beginning that should be marked. And because of that, we are not touching the object itself. The whole information about the mark state of object is inside the mark array. The question for you, maybe you have an idea why it is 16 bytes. Why it is 16 bytes? That is just not for, I don't know, 24 bytes, 26, 32, 100 bytes. Why it is 16 bytes? Maybe you have an idea why it is 16 bytes, why not any other number. In the meantime, Ahmed is asking, where is this mark array created, in managed heap or in a special region? Yes, it is a special region. It is inside the runtime. So the runtime keeps it as just a byte array inside byte array that is typical C++ array of bytes inside allocated inside the runtime, and the code is operating on that. By the way, I will show you the code for that. So yes, this is the internal data structure of the managed runtime, and so we can say maybe explicitly this is inside the runtime, and this is the managed heap itself. So the whole objects that we can allocate. An idea why it is 16 bytes? Just a last chance to win nothing, because I don't have any rewards for you, but just you know, satisfaction that you have a good guess. Somebody calculated that 16 bytes is the most efficient. It happens that there is a magic constant hard-coded, because some benchmarks show that they were good choice, but it is not the case in this. At least not the full through in this case. Alignment is not the case here, and yes, smallest possible object size. That's the good track. The smallest possible object size is exactly what we are considering here. So the smallest possible object size is 24 bytes. So we can say that, okay, 24 bytes is the smallest object size in case of 64-bit runtime. So the object cannot be smaller than 8 bytes fields, so 24 bytes. So we can say that, okay, 24 bytes granularity would be totally enough. Like we could say that we have 24 bytes granularity of the mark array, but it would be pretty problematic to calculate an offset inside, because if you would like to know in which particular byte we would be really interested to calculate, we need to take let's say this address, which is x, and split it and divide it by 24, and then we would have an offset inside a mark array. But dividing by 24 is not a super efficient operation. Let's say that in a kind words. So instead of using 24 bytes, we can use 16 bytes granularity. It is a little more than we need, but for sure 16 bytes granularity will cover every possible object that we can allocate, and obviously it will be super efficient to calculate the memory offset inside an array, because it is just the proper shift of bytes inside, so it is not a division in the end. So we can really efficiently calculate the offset inside a mark array, because we are using this 16-byte memory region. That's the story. I hope it is clear. So it is bigger granularity that we need in the end, but it is just so efficient in calculation the mark bit that it just pays off instead of worrying about that we are maybe storing a little bit more information that we need. So in the end, give me just a kind of feedback whether it is okay, whether you understand or not. I hope you understand. So 16 byte granularity is enough. It means in case of 64-bit runtime, we need 8 megabytes of Mark array for every 1 gigabyte of data, which is not so big overhead. Like if we have typical application using dozens of gigabytes, we will use up to 100 megabytes for a Mark array. This is not a huge number in the nowadays applications, so it is not so big deal. We need 8 megabytes of Mark array per 1 gigabyte of data. So this is a kind of short story because it was the easiest solution, easiest problem. So in the end, when we traverse the object graph and we would like to mark things during this object graph traversal, where we will be visiting objects, but instead of marking this here, we will mark this in the corresponding, oh, this is sorry for my drawing skills. We will just mark a particular bit inside a Mark array, and we will just mark here, 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 and we will have some bits marked for those objects that are reachable, and the rest will be just empty. So we will contain probably, we will have a lot of zeros in this mark bit interleaved with some occasional ones, saying that okay, in this particular memory addresses, under this particular memory addresses, we have the visited object. Okay, so that was the easiest one. Okay, how does it grow? Kevin is asking. Hello, Kevin. How the Mark array is growing? It, in general, the GC knows the size of the segments it is creating, so it is keeping this information and maintaining it. So this array is simply growing while the heap is growing. Maybe in these words will be the easiest answer. Yeah. It grows all together with the managed heap. It is not allocating it in advance, saying let's allocate it for 60, 24 or any gigabytes in size that you imagine you will be using, but it is growing all together with the managed heap. Another problem, the second one, the more difficult, is this graph traversal while the objects are being changed. So when we have two objects while we are traversing the graph, we may end up with various scenarios. So imagine you have one object, let's say it is A, and you have another object B, and obviously you have references between, you can have reference between them. And various things may happen, more or less severe for our consideration. So when we are traversing, first of all, the very first scenario, now I'm splitting the problem into smaller problems. So first situation that we can met is that not yet visited object has modified reference to some other object. So imagine we haven't visited A object so far, and it will change its reference to some other objects. That's fine, we don't care. Like, we will visit this object in the future, so we don't care what is being done there now, because it will be just visited in the future, so we don't care about the changes so yet, at least for this particular object. So this is fine. Another scenario is more problematic, is that we have already visited an object, and this object has removed some reference to otherwise unreachable object. So imagine the situation like I've described here, that we have object A that is just referencing some object B, and then it referenced object C while we were traversing it. But it may happen that, okay, but we have removed this reference after we have visited it. And now, whether it is a problem or not necessarily it is a problem. It may be that, okay, if this reference has been removed after we visited object B, that's a problem for, let's say, being GC more or less optimal. But it will just introduce kind of floating garbage. If it is just an object C not being references from any other place, it will be discovered as non-reachable in the next GC. So it is kind of suboptimal decision that, okay, that's why we are calling it floating garbage. It will be garbage collected in the next GC run simply. So it is not so problematic in the end. Yes, it introduces some suboptimal decision that, okay, we could maybe we could discover that it is no longer needed at the current GC, but we are living with that and we will just postponing this discovery to the next GC. So in the end, this is kind of fine situation. We just created some floating garbage that will be collected next time. Okay, one question regarding the marking, so I will just return. Why we are not using why then we are using MT for marking? Why then we are using method table for marking in not concurrent case? Why not using the header? Okay. Let me just, okay. I suppose it is decision related to the frequency of the and the memory access patterns. Method table is probably in the cache line, so probably it is already touched somehow. We have read it while the graph traversal, so we can modify it, and we can assume marking is much more often. Header is just a few is a pointer size before the method table, so it depends. It may be less frequently accessed. At least probably I believe we are we are supposing that method table part of the memory is already touched somehow and caches are warm, so we are just using it because it is more frequently accessed memory. I hope it answers your question. Okay, so return to our floating garbage situation. That's fine. Like, we introduced some overhead, but it will be just garbage collected next time. But it is the very first place when we see that the concurrent GC is a little bit less optimal comparing it to the non-concurrent one, because we have some inconsistency. The concurrent GC will leave some garbage, the floating garbage, that may be discovered only the next time. This is kind of obviously we need to choose between the speed, concurrency, optimal aggressiveness of the GC, and so on and so on. The next situation is that the already visited object has added reference to otherwise unreachable object. So, for example, imagine we have this object situation like here, that some objects has been already visited, and there is another object pointing to some object, and because the code is doing so, we change the references between some objects. This is one of the situations that you can imagine is describing this scenario. So instead of this situation, out of the sudden we have, okay, in the code we have removed these references and we assigned this reference. And this case, we ending up with this situation. We have an already visited object that now points to an object that is not reachable from any other place. It can be also if we are just assigning here a new object. So if you are creating a new object here, assigning it to a already visited object, then again we have visited this object, so we will not traverse it again, so we will not see that now it contains to a reference to a new object. So this scenario is much more dangerous. Sorry, trying to. So this is not fine, definitely not fine. We have the lost object problem. We have already visited some object, so the graph traversal will not visit it anymore. And now, after we have visited it, we are assigning some reference to it. But we will not notice that, obviously, because we have visited this object. And it means we will lost the information about this reference, and because we will lose this information, we will not visit it. We are just creating a very dangerous lost object problem. We will just lose this object. It will be not marked, it will be garbage collected, and the world will be exploding because we will try to use an object that has been garbage collected, because obviously this reference is valid reference, so we expect that someone will be using this object while it will be garbage collected. So yeah, this is not good, and we need to solve this for sure somehow. Then we have different scenarios. But we based on these three possible scenarios, we may build more complex scenarios. For example, a already visited object has added a reference to an otherwise reachable object. And now we need to traverse in the end the whole graph to know whether we have the lost object problem or not, depending whether we will have a chance to visit this other object or not. Maybe it was from this particular moment in time that it will be not visited, and so on and so on. So it simply means we need to track the reachability of this new object, the object to which we have changed the reference, to know whether there is a lost object problem or not. And also imagine that we are visiting an object. So currently visiting object has modified some references, and again it will just now depend in which point we are, whether this reference that we are changing has been already visited. If it was, okay. If it was not, okay. I mean, if it was not okay, if it was not visited yet, it is okay. If it was already visited, then it can be one of the previous problems. So in the end, it sums up in a pretty complex situation, like we really don't know what is going on, and we are trying to traverse the whole graph. The one question regarding that is what will be the result of trying to access such kind of the lost object problem. So what will be the result of the scenario previously described, that we will be garbage because of the lost object problem. We will just not notice that this particular object is reachable, so the GC will collect it in the next run probably, and then some code may try to access this memory. So it really depends, but in general GC is lazy in reclaiming memory. So in the end, what will happen, just to kind of a spoiler what is happening when the GC is doing its job, imagine that this is an object C and this is an object A, B and D. So they are in the memory. And okay, this is an object that should be live because it is reachable. This is reachable. This may be also reachable, and this has been not correctly discovered as not reachable, so we will reclaim memory of it. Which means GC will know that there is a gap here that can be reused. So in the end, typically in a non-compacting GC, we simply end up in the situation that GC knows, okay, this is a memory region that can be reused. It is a gap. But it does not clear this memory because it is not, it will be probably it will be not beneficial to do that now. So it is okay. Good point. The question box is yeah, okay. So in the end we have the gap, and which simply means GC will track this space as a space that may be reused. It doesn't clear this memory, for example, with zeros. In the end, typically this object still is there, so if some code will be trying to access this object, it may happen it will succeed because this object may be still there. However, it is not supported, obviously. It is kind of implementation detail. It will be there, or maybe it will be not there, or maybe the compacting GC happened and the whole thing is not true, because we will have a memory layout which will be like that. So it will be A, B, D, and now this reference, so this pointer, will start to point to an object D, a different object. So really a lot of various things may happen. Probably not access violation, probably it will be still a memory inside a managed heap which was not decommitted. It could be still used, but it also depends on many scenarios, so we don't know. Answering to your question, it is not trivial to answer what will really happen. But in the end, it may be access violation, it may be just reading some trash data which is now another object, or maybe it will be kind of access violation, depending on how the GC will decide to what will be the region, and so on and so on. So those are pretty low-level implementation details. We all like it, but not for today. So let's just stop at this point. Okay. Okay. Question regarding this: no early method table poisoning for the GC object. So in general the question is how the GC marks this space which now can be used. Okay, that's true that the method table is may be changed to something which is called the free object, but it will be only happening for the very first object in such a gap. This is the very first thing. Another thing is that the only method table may be changed, not the data, not the data itself. So still there may be some trash, even if you are changing the method table to something which is stating that this is now a free space for being reused. Okay, so solution. So coming back to our consistency view. Yeah. We have a lot of situations now we have covered. We know that there are some situations that if we have visited an object, if we have not visited an object so far and we are changing it references, that's fine. We will visit it, so we will discover what's going on. But the problem is with those objects that we have already visited and they are changing something. The references has been changed, and we may try to split all these situations into those more detailed sub problems, but in the end we may end up as a solution is, okay, so if an object has been changed because some references has been changed, we simply need to revisit it, right? It is the solution that is just coming to our minds. It is the simplest solution. If we have noticed that someone has changed something in an object that has been already visited, we just need to revisit it. Just need to revisit it. Sounds simple. And so this is kind of sub-optimal solution, we could say, because we are interested now in all modified objects, and which is not every modification of an object may be a problem, because some references may be a problematic change, some other may be not a problem. We can change a field of an object, not necessarily a reference, but there is a solution for that, simply saying, okay, we don't care. Like, let's treat every modification as a possible problem. So in other words, we can say, okay, the problematic set of objects is a subset of all modified objects, but we are tracking modified objects in the end. So every modification that we would like to track is an object that we will revisit. So in the end, the solution is revisit all modified objects, simply. So while the object graph is being traversed and references are being changed, we need to track all the modifications that happen, and in the end we need to revisit all objects that have been modified during our traversal. Sounds pretty easy in the end. So various algorithms we can imagine here to balance the amount of the floating garbage, the number of revisits that needs to be made, and overall synchronization cost, for example, what data structure we use to keep all those modifications in objects. And probably books can be written about that, but I will just describe you the solution taken by the .NET. And for that, in case of .NET GC implementation, we are using I saw one question on the chat and I started to answer in my head. So let's just me show you this question before I will move into the .NET implementation details. Is programming in functional way without any object modification lowering pressure of the GC then, since the modified objects are always 0? Absolutely yes. In general, GC for functional languages may be pretty simpler because they are theoretically, if it is a pure functional language, if it is a pure functional language, modifications are not allowed. Objects are immutable by default if they are implemented as such. So it reduces this overhead, and it also reduces other overheads of tracking references between generations, and I will return to that in one of the next modules. So yes, in the end, it is better for the GC to have a pure functional language from this perspective. I agree. Okay, so returning to that, how it is implemented in .NET, how we track all those modifications of objects. For that, we have a plain old good write barrier. Write barrier is just a kind of general concept, which is just saying when we write something, here is a barrier, here is a kind of code that should be executed when we do this writing. And in case of .NET, we are using write barriers here for a code when we assign references between objects. In other words, it is a code injected when we are using the reference assignment. So for every code like that. And yeah, in the end, it is even more. It is a code injected for every object modification. Every time when you access a field and modify its data, you are injecting a write barrier. And because of that, every time when you are writing something like that in your code, it means you are modifying your code. This injected code, which we are calling write barrier, will be executed, and it will be responsible for notifying that the source object, which is in this case this S, which is being modified, has changed. And the responsibility of this write barrier is then simply that this notifying is happening by adding it to something which is called WriteWatch List. This is the overall concept. So now we have some overhead for sure, because now every assignment between an object will induce that this write barrier code will be executed that is responsible for maintaining this WriteWatch list, which is an overhead. Obviously, this needs to be injected only during the concurrent mark phase, so we can be switched on and switched off only at the time of the concurrent mark. At least this is good. And in the end, if this after all this traversal has been ended, we can use this WriteWatch list as additional routes to revisit every object that is inside such a list. And this is also answering your question, Rafał. Yes, so if you have a functional code that is not modifying your objects, your WriteWatch list will be empty, so you will not have any objects to revisit at the end of the concurrent mark phase. That's good. And also, still there will be the overhead from the runtime because the write barrier will be there trying to do it. But if you have a code that is not doing such modifications, then the write barrier code also will be not executed because we are not doing any assignment between objects. So this is in the end how it is working. With the help of write barriers, we are maintaining the WriteWatch list that is responsible for keeping the list of all modifications that were happening during we were doing our concurrent mark. If you have any questions, as always, do not hesitate to ask. So in the end, imagine that you have this graph describing the GC in the .NET. From the time perspective. So we have here the time, which is going to right, and there are two threads with the code. So there is thread number 1 and 2 executing some code, and there is for example the GC thread for the GC purposes. It is not so super important whether it is a GC thread or it is on another thread. But we have this situation here described. Here we have a case of non-concurrent GC. So everything was happening during the pause. So we are not covering this today. Today we have some concurrent GC. This is the whole concurrent GC. From this point to this point we have the concurrent GC. And it is containing with some phases. It contains some phases mostly because of this concurrent mark. As you see, there is a first pause here marked as A, and this is the pause responsible for doing some kind of initial stop the word phase. We need to start from something. So this A phase is an initial work that is being kind of preparation of the routes to be visited. Here we are just stopping our application, all the threads are suspended, and we are gathering the routes from the stack and finalization routes. To have a kind of consistency, because it would be really painful to scan stacks of the threads while the application is running. So we are pausing the application, scanning the routes, finalization routes, and we are then have some initial list to start from for the object graph traversal. Then we have B as the main concurrent mark phase, the main work described today. So the concurrent mark phase, as you see, is running with the threads being resumed. So okay, after this short pause of the initial work, we are resuming all the threads, the application is running, and also the concurrent mark is happening. And the main work is done here. So at the beginning of this concurrent phase, the B phase, we are enabling the write barriers to start tracking modifications of the objects and populating the WriteWatch list. Then the concurrent traversal happens, and the regular one as I described you previously, so we are just traversing object graph and so on and so on, using some to-visit list as also described last week. And at the end of this phase, we are revisiting objects from the WriteWatch list. just to try to catch up with all the modifications that happened. And it should be pretty okay. Like it seems, and now we will have a kind of consistent, almost consistent view of what's going on, what has changed, and so on and so on. So that's why the WriteWatch list is so important. Then, as you see, there is another pause, and we need it just to make sure everything is consistent and valid. It may be suboptimal because for sure B phase may introduce some floating garbage, but still we need to make sure that the results are correct, so we don't have any lost objects. And for that we are pausing the whole thing again, so we are now in the C phase, and the C phase is another stop the word phase. While the application is paused, we are trying to get the final true situation, what is to be collected. So this C phase is another pause. At this moment, the mark array should pretty well reflect the state of the application, because we started from the stack roots, we have done all the object graph traversal, we catched up with the help of the WriteWatch list. So typically at this point, if those references are not being changed as a crazy, it will pretty well reflect the true. But just to make sure, we again traverse from all the roots. So from the stack, from the finalization roots, from the handles. It sounds like why we are just doing again the same thing. We wanted to have a concurrent mark traversal, but now you are saying that in the end of this concurrent mark we are doing the whole traversal again. Yes, but we are not doing a lot of work here, because remember that the mark traversal algorithm, the object graph traversal algorithm is using the mark. It will be not visiting already visited objects, and the graph currently mostly has been visited, so this traversal would be pretty small here. We will just including some small paths here and there, maybe even not so big number will be visited, because most of the objects has been already visited. So this final traversal, although is non-concurrent and very similar to the one that I described it last week, it is a lot less work to do, because most objects have been already visited. And there is also some final bookkeeping. As always, we need to remember about dependent handles, weak references, but this is a kind of bookkeeping not so interesting for us for today. So in the end, this is how the whole concurrent mark is working. Initial work, just to gather roots from stack and finalization. Then concurrent mark, which is just traversing the whole graph and also keeping the list of modifications of objects while the whole thing is happening. And in the end, somewhere in the end, using this WriteWatch list as a additional roots to revisit, then small pause just to catch up every possible change that happened, scanning from all the roots, and then that's it. I'm seeing your question, Rafał, but it is pretty long question, so I probably will stay with this question to the end of the webinar, not to interrupt the flow of the presentation. And then we have the D, and D is just the concurrent garbage collection that I will be describing in a few weeks. I don't remember exactly where, but then there is this concurrent garbage collection happening. But the concurrent mark is here, A, B, C. Okay, And I hope it is just a little bit more clear how it is working internally, because this is exactly how it is working. Nothing more to add in the end. There are some ETW some events emitted while the GC is happening. So almost every stage of the GC emits some event, and the same for the concurrent marking. So in case of the B stage, concurrent mark, 2 events are being emitted. You can look at them with the help of, for example, Purview. You can start a session in Purview and look for event called BGC, which is background GC drain mark, and the revisit. And those are the single events, so there is a 1 drain mark and 1 revisit event per the concurrent GC. And as we see, it provides some information, like drain mark is an event information about the number of objects in an initial work list. So after this initial work has been done, this event will inform you how many objects you have in an initial work list, so how many references were on the stack and in the finalization queue. More interesting, maybe the revisit one is informing you how many pages were dirty and how many objects have been eventually marked because of that. I will just describe you why I'm using here a page concept, but in general this revisit event is saying that okay, during the concurrent marked there were number of pages discovered as modified, and in the end the whole object graph traversal of revisiting those potential routes introduced a set of new objects, and there will be information how much marked new objects were introduced because of the revisiting. So if your code is poorly functional, the revisit will emit an event with 0, because it will be we have no modifications between objects while the concurrent mark is happening. And if you are writing code which is changing references like a crazy, the revisit will contain a huge number saying while the concurrent mark was working, a lot of references has been changed, a lot of revisits happened, and a lot of new objects has been marked because of that. Okay. This is one thing. So we need to maintain the WriteWatch list to know what has been changed, and we know the concept, we know the write barrier is responsible for that or not, we will see. And the question is now how to implement this WriteWatch list. It is not trivial, as you may imagine, because it may be trivial, but the change between objects, so changing reference between objects, may be super common operation. So it needs to be super efficient not to introduce a big overhead. So that's because of it is not trivial. And how this WriteWatch list was then implemented. Then I need to cover some history, because historically .NET Core was ported from .NET Framework, as we know, which was Windows based. And because of that, the concept how the GC is working was a little coupled with the Windows itself. So for the WriteWatch list, they used the Windows API. There is an API in the Windows operating system called WriteWatch. This is a WriteWatch mechanism that allows you to keep the list of pages that has been modified. A page is just a basic building block. Every time your process, including .NET process, needs a memory from operating system, it cannot ask for a single byte. It is always asking for a page or set of pages. So the smallest memory region that the process may obtain from operating system is called page, and this page is 4 kilobytes. So in the end, your application is split into a big number of pages. And obviously the same for the managed heap. So when the GC is allocating managed heap for your objects, it is asking for a set of pages, and then it operates inside those pages. So in case of Windows, when the GC, the runtime, was creating the managed heap, asking for pages, it was enabling this WriteWatch mechanism. There was a single flag called mem_WriteWatch used in the virtual alloc call. And because of that, operating system was tracking modifications for the pages that has been allocated with the help of this flag. And at some point in time, in future, you could always ask the operating system for a list of the pages that has been modified with the help of the getWriteWatch call. So getWriteWatch was used simply as a WriteWatch list mechanism on Windows, because it was enough. Like, if you would like to know what objects has been modified, even without using write barrier, as you see, you could get information about that with the help of this WriteWatch mechanism. Yes, it is pretty not granular. Like, if you have changed a single object, the whole page will be marked as dirty, as modified, so then the whole page needs to be treated as a potential root, which means the whole page needs to be revisited, which means that every object inside such modified page needs to be revisited. This is a kind of overhead that we need to live with. So it seemed to be a pretty good compromise. Like, okay, we didn't need write barriers. We are really afraid of write barriers because they are injected in a regular code. Every reference assignment introduces write barrier overhead during the concurrent mark. So not having write barriers was super nice. Unfortunately, such an approach also produces pretty a lot of false positive roots. Every page modification invalidated the whole page. So even if you changed a single reference in a single small object, the whole page became dirty, and the whole page has been treated as a potential revisit source. That's not good. Moreover, because it was so coupled with the page concept, which is by default 4 kilobyte, it blocked a little usage of concept of large pages, because typically we are using the process which is based on 4 kilobyte sized pages, but there is also a concept of large page, which is, as far as I remember, 2 gigabyte. No, 2 gigabyte. I don't remember now. Let's imagine it is 1 gigabyte. It is less probably, but I don't remember now. So you can allocate a huge pages, which has some benefits. But if you would be using then a huge page, a large page, which is maybe for 100 megabytes. Okay, I will not guess, I will check. Then when you are using large pages, then you have even less granularity, because now even modifying a single object inside a large page will invalidate the whole large page, and megabytes of data will become a potential root, and we need to revisit every object from within such a large page. So it is not possible to use large pages altogether with WriteWatch mechanism that blocked usage of large pages. Okay, so that's the story of the Windows implementation. And then during the Linux port, there was a pretty big problem of porting the WriteWatch mechanism directly, because there is even a blog post from Maoni Stevens. She was not able to find any good counterpart API on Linux for WriteWatch mechanism. they tried to do some OS-based magic or anything, but it was not reliable. So instead of trying to mimic this behavior, they introduced the regular write barrier code for Linux version. So Linux was using this approach I described you, write barrier that was modifying and keeping track of WriteWatch List programmatically. WriteWatch List on Linux was just a data structure inside the runtime, and the write barrier was invalidating it when it was appropriate. Sorry. Which works so well that in the end Windows also uses it. So now the history is that it has been changed, and both Windows and both Linux versions are using the write barrier approach, and the WriteWatch mechanism is no longer used. It is used in the full framework. It is used in the .NET Core 2.1. I'm not sure about 3.0. Maybe it is or not. I need to check. So, okay, in the end we have this story that we have write barriers. It has some overhead, but it is okay enough to benefit from the other advantages. Because write barrier is the CLR code, obviously. The CLR, the runtime, is injecting the write barrier. So now the barrier and the maintenance of the WriteWatch list might be much more smart. Like, for example, even if you are modifying an object by changing some integer field of it, WriteWatch mechanism was invalidating the whole page because it was just a modification of an object. But it doesn't make sense to revisit an object just because a field of it has been changed, numerical field. So a write barrier may be much more smart and will just ignore such assignment, because we would like only to track reference changes, not every field changes. It is also much more flexible, so and we have bigger granularity. We can modify the granularity. For example, we can use parse, normal pages, large pages, whatever we like pages, and still you have a programmatically maintained WriteWatch list. They are now separate concepts. We don't tie the concept of WriteWatch with the concept of the page itself. And that also helped to introduce the large page support for the .NET runtime, which has been added in .NET Core 3.1 as far as I remember. So in the end, that's the whole story. We have this WriteWatch mechanism every time that assignment between objects is happening. So every time when you have something like that, we change the reference between an object to another object, or maybe to a new object. The write barrier injected during the concurrent mark is keeping track information about this change. And because of the efficiency that has been discovered as good enough, even in case of this programmatical WriteWatch list, it is still on the page size basics. So still, it is the page size, the whole page size, a memory region that we invalidate because of the modification of an object. But it is a good enough compromise, the good enough granularity as it turns out. So still we are invalidating the whole 4 kilobyte, but now in much more intelligent way. We don't do it for integer, for single types modifications, only for references changes. Okay, so that's the whole story. I hope that it explains you a little the concept and how we maintain this WriteWatch list, which is in the end a set of additional routes. So just to follow up, just to sum up the thing, and draw one more drawing from my side. Imagine that you have an object and it is pointing to some object in another place. This object lies within an object, let's call it A, and then we have object B and object C. Okay, object A points to object B. But object A lies within some memory region which is 4 kilobytes in size. Obviously, every object is in some memory region, and it is split in 4 kilobyte in size memory regions. So concurrent mark is happening. We started this phase of concurrent mark. We switched on the write barrier, and now we are just saying, okay, in our code, let's, for example, assume that we are doing something like that. So we changed the reference. So we changed this reference to this reference. And the write barrier, which is injected when executing this assignment, is now discovering obviously this and saying, okay, so we have changed the reference from object A. So we need to invalidate the whole page, and now we are marking this page as dirty. And it means that at the end of the concurrent mark, the whole page will be now treated as a potential source of roots that needs to be revisited, including all the objects that are there also. Maybe they were not modified, even most probably they were not modified, but we don't know. This is the granularity that we are just agreed. So we will now treat every object inside this particular memory region as a potential source to revisit. So we will start traversal from A, from this object, from this, from every object lying inside this page size memory region. That's the story. I hope it summarizes this slide a little. Okay. If you have any questions, do not hesitate to ask, as always. Because we are slowly ending. Again, 1.5 hour will be probably the length of this module. So just inside the code, because we are always ending with some examples of the code from the famous GC CPP file. So if you would like to investigate the code of the whole story of the concurrent marking story, there is a background mark phase, which is exactly that. It is called background. This is one of the names pointing to the concurrency happening in the GC. And there are 3 most important data structures used by this method. There is this mark array. That is exactly what I described, the continuous memory regions for the bits, for marking objects. There is a background mark stack array. This is the concurrent version of the to-visit list. If you remember, in case of the non-concurrent version, there was a mark stack, the stack of the objects addresses to be visited. Here we are using the concurrent version, which is called background mark stack array. And there is also CMark list, which is just this initial work list discovered during the initial phase. So it is a list of the initial routes from which we start our graph traversal. And here we will be seeing, for example, that, okay, CMark list is being populated in the background promote callback method, which will be called by all the routes discovered from the stack and finalization queue. If you would like to see the marking of the objects, there is the background mark object method that is commonly used during the whole thing. And in the end of this mark phase, you can see emitting this drain mark event that I described it to you previously. Then there is this pretty important feature flag, which is called use software WriteWatch, which is exactly the story I've described. Instead of relying on the Windows API, we are relying on the internal software implementation of the WriteWatch mechanism, and this flag is now defined for Windows and Linux. And you might see usage of write barriers because they are also part of the runtime, obviously. So for example, we can search for this particular write barrier. So let's just find it in the Visual Studio. Just to show you some magic code from inside the runtime. It takes some time. So here we have the code, and the write barrier code is written in assembly because it needs to be super efficient, so we don't rely even on the compiler, but we are just hand coding the assembly that needs to be injected. And here we have this particular code, write barrier for 64-bit version. And we will see here the very first line of the write barrier is the operation itself that we need to do. This is the assignment of the reference. So we are saying, okay, we are assigning this reference because this is the goal of the whole operation. But additionally, we are keeping track of this. We are keeping track of the WriteWatch mechanism. You will see this patch label thing inside write barriers and other stuff injected by the runtime with these strange addresses. This is a kind of placeholder. This is a placeholder of an address of a mark array. So during the runtime works, when it will be injecting this write barrier, it will take this assembly code, it will find this patch label, and it will replace this hard-coded strange address with the proper valid address of the current mark array. So it will be at runtime patched by the proper address. And then we see this super simple calculation of the proper address inside a mark array, because it is just shifting it by proper number of WriteWatch List. Sorry, I'm saying about WriteWatch List, obviously not mark array. It will be just an address of the WriteWatch data structure, and we are just shifting it by the proper bytes to have this page size granularity, which is 12 bytes. To have the page size granularity, which is also super nice to calculate fastly. And if it will be just not set yet, it will be set to maximum byte value, because it is a byte granularity that we are using here in the WriteWatch list, because it is efficient enough. Like byte granularity is okay for this particular scenario. This is the code of the write barrier that we are describing. Using the WriteWatch list, address of the WriteWatch data structure being replaced at runtime, calculating the offset within this array, and then setting it to a once, as just saying, okay, this particular page is dirty, and then it will be interpreted by the runtime correctly inside the revisit written pages method. It will be just using the same data structure from the perspective of the GC. So the write barrier is in setting bytes inside this data structure, and then GC is looking at the get WriteWatch for GC heap method, which is just using the same data structure. In case of the Windows, which is not and the older version, which is not using this flag, we will see the call to the get WriteWatch mechanism to get the WriteWatch if we would like to use it. Okay, and that's the very last slide. The super low-level part of the concurrent mark phase is this concurrent marking that is happening inside the background mark simple or background mark simple 1, which will be just consuming the background mark stack array to consume and populate the to visit list, and then the mark array bit is changed inside the background mark 1 method. Let's just look at it as the last thing. Sometimes probably I will dedicate one single hour for traversing the whole code, but it is not so important probably now. So background mark 1 is the one which is exactly doing that, marking the mark array, and as we see, it is just a code operating on this mark array, setting a single bit, and mark array is just a number, just a regular array, nothing super sophisticated, a regular array which is just properly interpreted on the bit level. So that's the whole magic. Looks really innocent, but it is a pretty powerful feature. Okay, so that's the whole story from my side. I hope it explains a little how it's all working. Obviously those slides will be available, so you can follow the code if you would like to get even deeper inside the whole thing based on the thing that you have learned. Again, if you have any question, do not hesitate to ask. I see at least 3 questions that I haven't answered so far, so let's see what you have prepared for me. The very first one from Laszlo is the question: is the mark array updated when compacting Gen 1 or Gen 2? Yes, but as maybe I was too fast in answering. Remember that mark array lifetime is only during the mark phase. So it is needed for discovering what is reachable. But after that, we are consuming this information for the garbage collection itself, and we are discarding this information. So in the end, after the GC, we don't care about the mark array no more. The new mark array with proper bits will be populated in the next GC. So probably I was too fast answering yes, because we don't care. Like we consume the information for planning, we use this maybe for compacting, but then it is discarded information and will be repopulated during the next GC, because then we need to discover again the information, what is reachable or not. This is the same story as in case of non-concurrent GC. The mark bit is cleared after the planning phase. So in the end, after the GC, the mark bit is cleared and we don't know what is reachable again. We need another GC, we need another mark phase to discover that. I hope it answered your question, Laszlo. Next question. It might need some measurement. Allocating is firing GC. Yes, allocating is firing GC, that's true. When you are not modifying objects, you sometimes need to reallocate it with new values. I need to get my head around this. When you are not modifying objects, you sometimes need to reallocate it with new values. Rafał, if you can rephrase this question maybe, because I'm afraid of not answering properly, because I'm not sure if I understand the question. So if you are still with us, please maybe say this in different words. Maybe I'm a little bit tired, so I will try to answer again with a rephrased question. Oh, you even rephrased it. It is cheaper not to modify or modify it but allocate. In general, I would say always allocating is more heavy than modification, because if you are not allocating and only modifying objects, you will not trigger GC. Modifying objects will not trigger GC, so but allocating may trigger it. So this is pretty often an approach that you are just allocating bunch of objects in advance and operate on the pool of those objects, and then you don't care, because unless GC happens and, for example, there is no concurrent GC, there will be no write barriers. so you don't care about the overhead of it because there will be no write barriers being injected. So modifying objects by itself doesn't change anything from the GC perspective. Almost. There is also this tracking of references between generations, and we will return to that, but still it is less costly than allocation, I would say. So I would prefer to not allocate and prefer modifying already allocated objects. Okay, then the next question: is the mark array mapped back to the object's meta table for the planning compacting? In the end, it is conceptually the thing. So then when we are planning, then we look at the mark array to know where there are those objects that are reachable, and gathering into things that are called plugs, and this will be covered next week. So the whole planning phase will be next week, and the planning phase is using this information object by object in the end. So yes, this is somehow mapped back to the objects itself. Okay, question, returning to your question, concurrent gen 0 is not happening. My question is if we have a concurrent gen 0 GC during no, during the background GC only non-concurrent gen 0 can kick in. So this is the simplification, not to concurrent too much. If there is a background GC, so as we had this on the slide, if we have a concurrent GC here, for example, or here, and because of allocations, we need to clean up a little the gen 0, the background GC will be paused and the foreground GC will happen, but this foreground GC is a non-concurrent one, the simplest one. So we could try to make it probably even concurrent one, but in general Gen 0's GCs and Gen 1 GCs are always in .NET non-concurrent, because it's assumed they are fast enough to make it non-concurrent, make it optimal in terms of the memory reclamation, and don't care about the overhead, because pauses should not be long to be worried about that. So I hope it answers your question. And Christoph, I see you managed to stay long enough today to ask a question. I'm super happy. So in the final stop the word phase C, why revisiting all routes instead of just one? Because there is always this slow inconsistency that may happen. We have at the end of the B phase, we are revisiting objects from the WriteWatch list, but during this revisiting, the application is still using. So you could have some inconsistency. So to end up this endless loop of trying to catch up, you need simply to stop and look around and try to and catch up simply when no one is interrupting, because there is this only small gap of time that you could get some inconsistency. Yeah, that's the answer, I hope so. And sorry for delaying your dinner. Then I hope we will see. Maybe in the next episode will be a little bit shorter to have a possibility to have a dinner with your family. Yes, so in the end it is not happening during the stop the word phase. That's the thing. The revisiting the WriteWatch list is not during the stop the word phase. It might be surprising. Okay. Okay, Laszlo has a question now rephrased. So the question is about whether we need to, about the mark array, do we need to update if we have a Gen0 GC during background GC? That's pretty nice question, pretty deep one. Whether we need to update mark array if we have Gen0 during background GC. I need to think a little. If we have background GC and then we are pausing our application and all the threads because we are kicking in with the foreground GC, and then whether we need to. Good question. I'm afraid of having a definite answer now because it is recorded and will be just watched by the millions of .NET developers. My first feeling is probably we need to have a consistent view, but I need to dig in. I will check it because it is a pretty nice question and I'm not sure what is the answer now. So it's one of the questions that probably I will answer next week, for example, all in a kind of follow-up blog post. Nice question, Laszlo. I'm always learning. Okay, so I'm slowly ending then because Chris is waiting for his dinner. If you have any other questions, you can always catch me on Twitter. The Konrad Kokosa handle is there waiting for you. I hope now you'll know a little bit more about concurrent marking, because it is pretty nice that it is able to do that, and this is the only concurrent phase in the GC. So as I said, concurrent mark is possible. Sorry, maybe that was not fortunate phrasing. The concurrent mark is happening here. Here concurrent sweeping is happening that I will describe after a few weeks. The concurrent compacting is not happening currently in .NET. So this phase is only a sweep one. We will not compact memory. The GC currently in .NET is not able to do that. But we will return to that for sure. It was our very first contact with the concurrency in the context of the .NET GC, how it is able to do things while the application is running. If you don't have any more questions, then let's not delay things too much and too long. Next time we will be just covering the plan phase. Super interesting. One of the less detail described in the blog post because it is pretty internal one, and because of that I like it very much. I had a super nice satisfaction discovering all this stuff because it is so not popular in the documentation that by debugging the GC I was able to discover all this stuff, which was super satisfying. So for now it is today, and for today it is enough. Thank you very much for being with me. See you next week then. Have a nice day, have a nice dinners, breakfasts and other meetings depending where are you living and where you are now. Have a nice day then, and remember about the Steam Fest, which is now happening on Steam platform. If you are playing games, probably there is a lot of nice things to do now there. So have a nice day, bye, and see you next time, next Wednesday.